So I am having a heck of a time getting this video recorded. So I'm going to do it differently than I've done it before. So I apologize for kind of the builds, but I'm looking at your review sheet. These are, of course, trying to get you ready for your Unit 3 exam. And one of the questions is, what is the power behind our sun? And of course, it's nuclear fusion. And we've been talking a lot about, we're about halfway through 10 billion years worth of hydrogen, plus hydrogen goes to form helium and a lot of energy. Let's see what else on your test. So I'm going to ask you, so this is a little bit about the two types of nuclear reactions. So this would be, this is the helium plus helium goes, sorry, hydrogen plus hydrogen goes to form helium and a lot of energy. So this is actually called nuclear fusion. Nuclear fission is being shown here, where you have a big atom, like uranium's great at doing this, and actually it falls apart and you get two smaller nuclei of atoms, and so this is nuclear fission, and this will actually also create energy. What else do we have? Oh, conditions required for a nuclear fusion to occur. We need to have very high temperatures, which we only have in the core of the sun, the high enough temperatures, in addition to very high pressures. So this is kind of showing an unsuccessful two hydrogen atoms are not getting together, and this is showing you where they are getting together at high temperatures and high pressures. I think you can just ignore this. I don't think there'll be a question over that. There will be a question over hydrostatic equilibrium. Anytime you see equilibrium, you should think of like the equal sign. In this case, the two things that are equal is the pressure, the outward pressure associated with what we just talked about, associated with the energy created during nuclear fusion in the core of the sun, versus the inward pressure of gravity. So if these two are equal, the sun is not getting larger, nor is the sun getting smaller. So our sun's about the same volume for a while. There is a question about this random walk. I just think this is so cool. And I'm not sure what form it will take, maybe a multiple choice question, but it takes about 100,000 years for this energy, this is photon energy, to work its way out, most likely through what we call the R, radiative zone. I just think that is so cool. Okay. So there'll be a question about solar wind, and solar wind is where I go. So when the sun turned on about 4.6 billion years ago, it created this kind of outward pressure of moving material, moving photons, we call solar wind. Heliosphere. So heliosphere, if this is the sun and you think of that basically outward pressure out, one of the things we know is that it's going to get weaker and weaker, right? So out here at some point that solar wind kind of peters out. So the area I've drawn is actually the edge of the heliosphere. So yeah, it's way far out there though. I believe it's beyond the Oort cloud that we talked about earlier in the semester. You'll need to know the three layers of the sun's, let's see, here they are. The three layers of what we call the sun. I'll put atmosphere here. Okay, and you'll need to know the three layers of the sun's interior. I'm not going to go over them now, but be able to know just a little bit about them. I would jot them down on your card. Let's see, granules. And they kind of remind me of kind of like a honeycomb, like bees go in and out of these things. But granules are always there. When we look through the telescope at our sun lab, we did not see granules on the solar disk, but they were there. They are these kind of moving, sort of irregularly shaped features where the bright area, like this says, represents where the hot gas is coming up, and hot gas or plasma, and then the dark regions on the edges are where the cooler gas is sinking. So we actually said that the outermost layer of the sun's interior is the convection zone. And you can kind of see a little bit of convection going on there with hot rising and cool sinking. Let's see, but solar granules are always there. relative temperature of the sun's atmosphere. And it's really weird that that the photosphere is closest to the sun's. This is the core clear down here, and then we have our other three layers. So the photosphere and the convection zone actually butt up against each other. But the outermost layer of the sun's atmosphere actually is the highest temperature. It's the corona. All right, then we go on to the next part. Space weather, I think here in a minute I call it space weather, solar weather. They are the same thing to me. That actually is is the sun sending an extra dose of charged particles or not. So that gets to this idea of an active sun versus a quiet sun. So ongoing features, so I told you that granules, solar granules are always there. Also supergranules, spicules, and solar wind, always there. What is not always there are these things associated with an active sun. I've listed them here: sunspots, splotches, filaments, prominences, coronal holes, and the granddaddy of them all, this is the biggest one, coronal mass ejections. So these are all associated with an active sun. Let's see. What is the most energetic of the solar events? And I said I have a star next to him. This is the most energetic. Most energetic. By this I mean the coronal mass ejections. All right. Well, maybe that's where I have coronal mass ejections. That's this guy right here. And we kind of talked in lecture that, well, it depends on, is the Earth in the path of this ejected material or not? All right. Space weather. Space weather, solar weather means the same thing to me. Like I said, if the sun is active, then actually it is, like I said before, we have all these different things going on. An assortment of, depending upon its activity. Let's see, what else do I have? Maybe that's about it. The kind of follow up to that, this is our northern lights. Northern lights, actually in the southern hemisphere, guess what? They call them southern lights. So actually, the closer you go to either pole, if the sun has been active and spewing charged particles, those charged particles can actually cascade then down the polar regions, because the Earth's atmosphere can protect us against some normal charged particles from the sun, but if it's extra active, those charged particles come through. Let's see, cycles. You're talking, I think, probably a multiple choice question about how long does it take for the sun to kind of ramp up and then kind of come back down from its active period. And the solar cycles generally are 11 years. And then the reason we have these kind of 11-year ramp up and then more of a quiet sun has to do with the sun's magnetic fields. And we saw a video on this. It's almost like it's playing Twister, where it's crazy rotation and charged particles make these odd sort of, this is a sunspot right here, these odd sort of magnetic fields that just get all twisted up, and then they kind of break and it starts all over again. All right, on to the next part. Star's luminosity. So luminosity means, in general, kind of the energy that a star is putting out. And that's what luminosity means. So luminosity is, when we talked about the distance and all that, luminosity is kind of more of a scientific, it's the energy it's pumping out. It has nothing to do with how far away the star is. So, is that what I have? Yeah. And maybe this slide can also answer the next one. I have, why does the apparent brightness change with distance? Remember, apparent brightness, I guess I should define it. What does it mean? It means what the star appears to us. And it's kind of like this is trying to show you, if this is where your light source is, if you get, of course, AU is astronomical units. That's how far the Earth is from the sun. If you get farther from the sun, okay, that same shaft of light is going to be diluted, and it's diluted by what we call the square of the distance you move from the sun. So it makes sense. The farther you get from an object, the less bright it appears. So the apparent brightness goes down. We use the symbol m, lowercase m, for apparent brightness in astronomy. All right. And this was the don't blame me sort of thing. Hopefully we're all on the same page that the more negative the number, the more bright the object is. So this is apparent brightness, lowercase m, so that's very bright. And this actually is relatively dim. A +6 is less dim than a negative 1.46. Actually, the +6 is kind of the, like the slide says, if your eyes are good, nice dark skies, about naked eye, what you would see things. And then I want you to be able to explain this other scale. Dun, 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 capital M, and it's absolute, not apparent, absolute magnitude. And with absolute magnitude, what we do, and I try to describe this in class, is if this is us, we basically line our stars all up at the same distance, and that distance is 10 parsecs, which is about 32 light years away. So if they're the same distance, then we should, this is my eye right here, okay, we should actually, however bright they are, actually has to do with how much energy they're pumping out. So as it turns out, and I try to describe this in class, this absolute magnitude, M, big M, actually is directly related to the luminosity of the star. All right, there it is. Okay, on to classifying stars. So I think there's going to be a question on your test about this, that there are 7 spectral types that these lovely ladies came up with, and this is the hottest is the O, and the coolest is the M type. So I think that's kind of what this is to remind me of. All right. So here is stars. This is a distant star, or maybe a relatively close star. I can't tell from here. But if the star is moving, this is kind of the main movement of the star. We can kind of break it down into it moving away in a direct line. Now, if it's moving away in a direct line or towards us, we can actually use Doppler shift, Doppler effect. Remember, if it's moving towards us, oops, sorry. If it's moving towards us, you guys told me you're going to get a blue shift. Away from us, it's going to be a red shift. If it's moving side to side, which is what we call proper motion, then we are in good shape to go ahead and just use its relocating, okay, against the background stars. So those are 2 ways of checking on the motion and the velocity of a star moving. Speaking of stars moving, this is the Big Dipper, which we all know and love as it is today. This is what it was 50,000 years ago, and this is what it will be 50,000 years from now. So enjoy it while we can, right? This is my little heart here. And the point here is that these beautiful constellations that we all know and love, the stars kind of have different things in mind with regard to kind of how they're moving in their vicinity. So you can kind of see that. All right. So I see, what is this? Using parallax to determine distance to stars. So kind of get a handle on this, right? Parallax, we've looked at this before. Let's see if I can make this big. I think I can. All right. We've looked at this before. I don't think I can draw on it though. Here on the left, we have a relatively nearby star. The blue circle down here is the Earth's orbit, 6 months apart. So for a relatively nearby star, we're actually going to see it change against the background stars when we are 6 months apart. Okay, so in July the star is going to appear here, and in January the star is going to appear here. So now this actually angle is called what we call the parallax angle. So if the star is even closer, so this is nearby, that's weird, and this is even nearby, a closer star, check this out, as the Earth orbits the Sun 6 months apart, the closer it is, you would say, the bigger the parallax angle. So kind of be able to describe how we can use this kind of relocation of stars against the background stars as we orbit the Sun, called parallax, use that phenomenon to get a fix on how far away the star is. All right. And in my notes, since you're listening to this, I actually am going to focus on eclipsing binaries. So you'll have a question on there. All we mean by eclipsing binaries is that you don't, by the way, most stars, this is about half of stars. I've heard 2/3, but this is about half of stars actually have a companion, at least one companion. But we can't always see them. We can't always, what we say, resolve them as two stars. They're not all visual binaries. So one way that we can see that we have two stars is to check out the light curve. And we kind of talked about that. We actually see the light go up as both stars are visible, and then go down as one star goes in front of the other star. Eclipsing binaries. Let's see, what else do we have? All right, on to plotting stars. So HR diagram, H stands for Hirschsprung, R stands for Russell, and these dots actually then are stars, right? So an HR diagram, I kind of want you to be able to get your bearings. What do we plot along the x-axis? We plot temperature, okay? Oh, be a fine guy or girl, kiss me, where we have the hot stars over here, we have the cooler stars over here, versus luminosity. So this is really bright. This would be the absolute magnitude, okay, and these are dim, okay. So, and then we have the three general regions. What I circled here are called the main sequence. Up here we have our giants, supergiants, red giants, and then down over here we have our white dwarfs. So kind of have a sense for that, how that works. Let's see. How will our sun evolve? Well, our sun actually is about here-ish. Our sun is going to become a red giant. It's going to come over here, do a what, and it's coming up here in a minute. Planetary, sorry if that's not planetary nebula. Oh goodness, I butchered that. Planetary nebula, and then it's going to cool off and become a white dwarf. So that's generally speaking what our sun is going to do. And actually this is kind of showing you in comparison that our sun is going to, well, I don't know what this is doing. This is slide shouldn't be here. All right. So kind of finishing things up, we talked about the fact that the least massive suns are 0.08 solar masses. The most massive suns are 100, I think he even said 150 times the mass of our sun, the most massive suns. Sorry, most massive stars. I have down here differences in lifespan based upon mass. So that's coming up here. I just think this is pretty cool. That, yeah, the higher the mass, so if you take not our sun, but a star that is 10 times the mass of our sun, notice that it's not going to live for 10 billion years, it's going to live for 10 million years. More massive, it ages faster. If you take a light star, that's 1/10 times the mass of our sun. Instead of 10 billion years, it's going to be 100 billion years. So I don't know if I would want to live that long. All right, so the next one, stellar nurseries. A molecular cloud, I call it a giant molecular cloud, but a molecular cloud, it's the same thing. It's basically a humongous nebula where you can have lots of stars that are born about the same time. How a star forms from a nebula, I think that's the next couple of slides. So I generally would kind of know how a star would form from a nebula. And actually, this isn't just a star forming within a nebula. If it's a molecular cloud, which is a humongous nebula, which is being represented here, you actually have all sorts of stars that can be born in the same area. It gets some sort of regions that sort of kind of condense, pull together. And this slide kind of shows you two. Maybe not. I kind of like this one. Well, between these two. This material pulls together. It then ultimately, just like the story of our sun within the center of our solar nebula, the sun, how the sun came to turn on. That's basically how stars turn on. All right. So there'll be a question, maybe a multiple choice question, I can't decide, about the two types of clusters of stars. This is an open cluster, and this is a globular cluster. And Mrs. Snipes' favorite type of object to look at are globular clusters, I think. Although nebula are pretty darn cool too. Open clusters are relatively young stars, and they're kind of spread apart a little bit. Globular clusters are close together, and they're relatively old stars. So I probably know that too. That might help us later too. There'll be a question on there about brown dwarfs. Brown dwarfs are a failed star, basically. And the reason they failed was that they were less than, where's my less than 0.08 times the mass of our sun. So basically they didn't have enough mass to go ahead and get the conditions in their core to create nuclear fusion. Aging stars, well, it kind of depends upon mass. The low, let's see, if this is an HR diagram, these are the main sequence. Down here, these are your red dwarfs. And there'll be a question on there about red dwarfs. They're, like I said, relatively low mass stars. And the cool thing about red dwarfs is that basically they convect out their hydrogen. Wait, no, sorry. Yeah, sorry. No, they convect out their helium, because in the core they're taking H plus H goes to form helium. So basically what they do is they get that old helium out, they get fresh hydrogen in. So they're just kind of a gentle giant in that way. And so that's why they last so long. All right, the next several slides deal with this idea of, this is an HR diagram. We see temperatures down here. This would be O, this would be M type stars. And we talked about the different types of this red line would be the main sequence. And here actually you see the, I think this one's trying to show you that we see the high mass, high M, and this is low M, like for low mass. These guys arrive first, and I think you guys might have told me that these guys kind of take a little bit longer to arrive at the main sequence. So the point here is we can look at a cluster of stars. Each dot represents a star. We can look at cluster stars and get a sense for how long that cluster has been around. So if we compare, we call this one A and this one B, B actually has, to me, well, it's kind of hard to, it's kind of hard to tell, but it looks like actually A might be older because these guys are missing, because actually they have moved over here to the giant stage, or red giant, supergiants. And B still has these guys there. Anyway, yeah, because this one has 4 million years versus 3 million years. This, this one is showing you another cluster, and I think on here it talks about the turn-off point. Maybe it's on the next slide. But the turn-off point is kind of showing you where these stars are leaving the main sequence because they ran out of hydrogen. And we talked about earlier where these high-mass stars actually live their lives fast. And so they are going to turn off the main sequence before the low mass. And this is a good one. This is the turn-off point, okay? The lower the turn-off point, the older the cluster. Okay. All right, so here we don't see the dots, but this solid line is to try to kind of show you where kind of the dots or the stars would be on those HR diagrams, where this one is the oldest, and this one is, well, this one would be the very youngest. I don't know. All right, so there will be a term on there, planetary nebula. A planetary nebula through telescope look beautiful. Planetary nebula, you can see on this HR diagram, is at, and our sun will give off hopefully a beautiful planetary nebula after it consumes the Earth. So basically, it's nice and swollen, and the material kind of just drifts off, and then it's gonna cool down to become white dwarf, but it still will have the material in that before it cools off to become a white dwarf. Did I say it? Are we all on the same page? So this material is the material that was associated with the star, kind of in its outer edges, and it will kind of slough off, okay, and it will glow for a while, but glowing even longer would be kind of the core of our star. Well, it's not the core of a star, but the central part of our star, called a white dwarf. It will be in the phase we call a white dwarf. I know this is a very busy slide, but I'm pretty sure this is just to kind of remind you, when we talk about high mass stars, we're talking about something that is greater than 8 solar masses. And this slide kind of tells you a little bit about kind of the complicated, gives you a sense for the complicated sort of nuclear fusions that are occurring within that star. And this one, again, a busy slide, but I'm pretty sure I just want to emphasize that where it goes, see if this is right here. Okay, inert iron core. Inert means like it's not reacting, it's just sitting there. When the core is, when silicon plus silicon goes to form iron, well, I don't know silicon plus silicon, but silicon fusion goes to produce iron, iron cannot fuse. So my question is going to be, what is an iron on the periodic table? Actually, that's the highest, the most complicated atom that with the highest number of protons in the nucleus that a normal star can fuse to create in its core. All right, what do I have in my notes here? Supernova. Well, I guess I don't think it's going to be too complicated of a question. We didn't get to, there's two types of supernova, so I'm only going to ask you about this one supernova. Again, if something is more massive than 8 times the mass of our sun, it's going to end in a supernova. And what happens is it's an explosion that creates, this is my, looks like another nebula, isn't it? It's a special nebula called a supernova remnant, okay? And then in there, right there, we talked in class, and it's on that pretty colored sheet that you got, the little nubbin that's left is either going to be a neutron star, or a black hole. So it is going to leave something, but it's going to be one of those two things. So I hope that works for you. And supernova, this is just to try to kind of show you, not sure how the question is going to be formed here, but this is the brightness. Remember, magnitude is brightness, apparent brightness of the object after it goes supernova. So right here would be very bright, and then it kind of dims down over time. So I do want to, there will be a question about the neutron star. And as I said just a minute ago, when a star goes supernova, you're either going to have a neutron star or a black hole. And neutron stars, I know I said in class, are material is made up of a very compact object, and it's so compact, and I think I might have said it's like your wrapping paper. You squish, 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 squish. So basically, you have squished it so much that the atoms become deformed. Think of it that way, and the pressure and the squishiness basically has made your electrons and your protons morph into neutrons. It's just amazing. So it's like neutron soup. So I'm not sure how that question's going to go, but a neutron star then sends a signal called a pulsar. So pulsar is the blip, 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 blip. Okay, I think, oh, maybe I didn't have it. Maybe that's all. Okay, then we just talked briefly about stars with companions, and depending upon kind of where the companions are, they can have different things going on. So this is actually a retired WD for white dwarf, and this is kind of a star that is bloated, like our sun is going to be, and it can, if they're close enough, the material can transfer from the bloated one onto the retired white dwarf, and so it can actually create the conditions what we call for a nova event to occur. And what a nova event is basically, and kind of showing you, this is being dumped, material's being dumped on. Here's my white dwarf, and the material in what we call the accretion disk, that little frisbee area around the retired star, actually gets hot enough. I know it sounds kind of crazy, but it gets hot enough because of that friction and pressure sufficient that basically it begins nuclear fusion, but it's all at once. And so right here you can kind of see that nuclear fusion happening all at once. The nova events appear bright to us. They release a lot of energy, and they basically they blow off the material that had been gathering. And so I kind of likened it to blowing off your blanket. The cool thing about nova events is that they can reoccur because like I said, you can, you know, after you throw off your blanket, you can get your blanket back on again. So they can actually recover.